Welcome to today's STERIS Tech Talk on EO Residuals, Navigating ISO 10993 Part 7. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Maroot, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies. I'll be the host for today's event. Our presenter today is Jason Rogers. Jason is a Principal Scientist for STERIS AST, representing STERIS on several AMI committees, including Microbial Methods and Sterility Assurance. He graduated from the University of Minnesota Twin Cities with a bachelor's degree in biology. Jason has over 15 years of experience in the medical device and contract laboratory testing industry. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Jason to begin the presentation.
Thank you, Ashley. Hello, everyone, and thank you for joining us today for this STERIS Tech Talk about navigating the requirements of ISO 10993-7 for product ethylene oxide and ethylene chlorohydrin residues. In this webinar, we will discuss the different product patient contact categories, the associated category limits, and how those limits are determined. We will cover the extraction methods for determining residues, as well as considerations that should go into the design of product residue testing. Additionally, we will examine newer requirements around special patient populations. And lastly, we will discuss how aeration times are determined and how packaging and other considerations can assist in reducing or removing residues. There are three product patient contact categories designated in Section 4.3 of ISO 10993-7. They have permanent, prolonged, and limited. The limits for these categories are based on a 70 kilogram adult, a CEF of 0.2, and a PEF of 1.0. Limited patient contact device category is identified for devices with less than 24 hours of patient contact. Prolonged devices contact the patient greater than 24 hours, but no more than 30 days. Permanent devices are based on a patient contact of 30 days up to lifetime use. The standard indicates this is 25,000 days or 68.5 years. These limits may need to be adjusted for specific product considerations based on the patient body weight and or specific applications with shorter use for the identified treatment. If multiple limited contact devices are used on a patient over the course of treatment, the device may also need to meet prolonged limits. ISO 10993-7 Amendment 1, published in December of 2019, provides instruction for adjusting the calculation of limits for special populations such as neonates and infants. The CEF, or concomitant exposure factor, is the number used in the calculation of limits to consider the use of multiple devices used at the same time. The typical CEF assigned by the 10993-7 standard is 0.2, representing 5 devices. If more devices are potentially used, then the limits would need to be adjusted accordingly. Currently in revision, ISO 10993-17 covers toxicological risk assessment and provides the default CEF. Proportional exposure factor, or PEF, is used in the calculation of limits to consider the duration of contact that the patient will encounter the device. Since a device may not be used for the full duration of the exposure category, This calculation has the ability to adjust for the patient contact over the full use of the device. The default PEF in the standard is 1.0, indicating patient contact over the full duration of the device use. Together, the CEF and PEF are used to determine a utilization factor. The utilization factor, along with patient body mass or weight, and the TI or tolerable intake, which is the average daily dose of a substance over a specified time period based on body mass, are used to determine the tolerable exposure. ISO 10993-7 Annex G6.2, G6.3, and G6.4 provide more information about how the tolerable exposure is calculated. ISO 10993-17, sections 6.3.2 and 6.3.3 provide more information on the calculation of the CEF and PEF. In this table, we have the limits for the different patient contact categories. These are the limits based on a 70 kilogram adult patient, approximately 155 pounds. The limits for the first 24 hours or limited contact exposure are 4 milligrams of EO per device and 9 milligrams of ECH per device. Average daily dose is determined for prolonged and permanent patient contact devices. The average daily dose is multiplied by 30 days to determine the prolonged and permanent exposure 30-day limit. The average daily dose for permanent devices is multiplied by 25,000 days for the lifetime limit. Again, these limits may change if a device patient contact duration differs from those specified. Calculating limits for special populations can be achieved by utilizing the corrections provided in ISO 10993-7 Amendment 1 and details in 10993-7 Annexes G and H. The default body weight provided in ISO 10993-17 are 70 kilograms for adult men, 58 kilograms for adult women, 10 kilograms for children, and 3.5 kilograms for neonates less than 1 year. The TCL, or tolerable contact limit, is based on the first 24-hour result and not the total EO and ECH levels. The TCL calculation requires the surface area of the patient contacting portion of the device. In place of the TCL calculation, product could exhibit a negligible irritation test per ISO 10993-10. The ISO 10993-7 standard also identifies certain devices with special limits. This includes lower limits for intraocular lenses, as well as higher limits for other specific types of devices. Note that ocular toxicity of ECH is about 4 times greater than the corresponding EO level, and intraocular devices made from viscoelastic materials that contain chlorine may need to be evaluated. As you can see from this table, many of these devices are allowed higher levels of EO or ECH residues. This is based on the exposure risk versus patient benefit from these types of procedures. Not all medical devices are required to meet the limits outlined in ISO 10993-7. The limits apply to devices that have direct or indirect contact with the patient. Annex C offers a flowchart for determining the device limits. This annex also offers information on product extraction method, simulated versus exhaustive, or the extraction conditions such as time and temperature. Some devices may have portions of a device that are limited contact, such as a delivery catheter, or other portions that are prolonged or permanent patient contact, such as a stent. These two portions would need to be evaluated separately for residues. Items such as carrier hoops, electrical cords, handles, etc., would not typically be included in residue testing as they do not have the potential for patient contact. Fluid pathways through device handles would require further testing consideration. Simulated use extractions are a single extraction of a limited patient contact device or portion of a device. This device could be cut up and immersed in water. If appropriate, the device may be tested by extracting the fluid pathway, either by recirculating water through the fluid path or by extracting it by filling the fluid path with water and extracting it in a static condition. Extraction durations for limited contact devices are based on what is typical for patient contact. The extraction temperature is usually body temperature, 37 degrees Celsius, or controlled room temperature. Typically, only the portions of the device that have patient contact are included. For prolonged and permanent devices, or portions of a device, exhaustive or repetitive 24-hour extractions are performed. Similarly, exhaustive extractions might include cutting up the patient contacting portions and immersing them in water, or the fluid path may be tested if appropriate. The temperature would again typically be body temperature or room temperature. After each 24-hour extraction, the water used to extract the device would be collected and tested by gas chromatography. The product would then be re-extracted for another 24 hours. This process would continue until the amount of EO and ECH in the final extraction is 10% or less of the initial extraction, or until there is no statistically significant increase. If the limit for the device is met within a single extraction, the test would complete. Headspace or heated 100-degree air extractions for EO may also be utilized for certain devices. In this table, we have some examples of how certain devices may be evaluated. Urine drainage bags do not need to be tested, as they are used solely for drainage and do not have direct or indirect contact with the patient. An IV set, however, would have indirect patient contact, as the contents of the IV would contact the patient and may be in contact for greater than 24 hours. The IV set would typically be utilized at room temperature and would be extracted similarly for residues. A cardiovascular stent, however, has a delivery catheter, which would be limited patient contact within the body, and the patient contacting portions of the delivery device would be tested at 37 degrees Celsius. The stent would have permanent direct patient contact within the body and would be tested by exhaustive or repetitive extractions at 37 degrees Celsius. An enteral feeding set would have indirect, limited, or prolonged patient contact depending on the length of use, and would be tested at room temperature. An enteral feeding tube would have direct patient contact within the body for limited or prolonged use. The device would be tested at 37 degrees Celsius by simulated use, single extraction, or by exhaustive, repetitive extractions depending on the length of use. A wound exposure device may have no patient contact with the delivery system, but the closure component, such as a suture, may have direct patient contact for either prolonged or permanent duration if it's absorbable. The closure component would be tested by exhaustive repetitive extractions at 37 degrees Celsius. A suction catheter has limited direct patient contact and would be tested by simulated use or single extraction at 37 degrees Celsius. An orthopedic implant would have permanent direct patient contact within the body and would be tested by exhaustive repetitive extraction at 37 C. Again, Annex C provides a flowchart that is very useful in this evaluation. Product release requirements can be determined during validation activities without a dissipation curve based on acceptable endpoint testing data, essentially continuing aeration until the product is below the allowable residue limit. Dissipation curve data could be used within calculations provided in ISO 10993-7 to predict when the product would meet the allowable limits if they were not met within the specified test aeration time points. Dissipation curve data would need to be obtained from 3 independent processing runs to establish repeatability. The graph shown here uses data created for this discussion. Looking at the graph, the gray line meets the allowable limit within 24 hours of aeration. The blue line meets the limit within 48 hours of aeration, but the orange line does not reach the necessary aeration. A dissipation curve could be established to predict the applicable aeration time for the orange line to achieve the allowable residue. Establishing aeration times off the worst case condition may not always be the appropriate course. Establishing aeration time from product process through a single cycle may be more appropriate for routine release than using the aeration from product process through 2 cycles to account for reprocessing. The necessary aeration for 2X product should still be obtained and proceduralized for when it is necessary, but not necessarily used for every routine run. Utilizing the nominal values rather than upper limits of the specified EO injection, dwell time, or other variables may be more appropriate. Controlled aeration is preferred over ambient aeration for consistency and control. Determining actual patient population use and corresponding labeling, and not applying special population limits for devices that would not feasibly be used on such populations is advised. If more than one product type is processed through the same cycle, setting the aeration time based on the worst case product can add unnecessary delays in aeration time for other products. There are decisions that can impact residue levels made throughout the development and validation of a device. The type of materials used to make a device can retain residues more or less readily. Glass and metals are known to not retain EO, while plastics are more variable. Bleached papers and chlorinated compounds could impact ECH or ethylene chlorohydrin residues. Product design can also impact residues. Long, small lumens, dead ends, or voids can hold residues. How products are palletized can impact effectiveness of aeration. If boxes are densely packed and palletized, residues may be harder to remove. Pallet wrapping materials could also have an impact in effectiveness of aeration, such as netting versus plastic film. The design of packaging can aid or hinder the aeration of product. Layers of packaging and large instruction packets make it more difficult to remove EO residue during aeration. Process parameters can also impact residues. Utilizing lower EO concentrations can aid in reducing product residues, as has been observed through our sustainable ethylene oxide program. Deeper vacuum pressures can be more effective at removing residues. Precaution should be exercised as this can challenge packaging seals, so ensure that the seals have been tested at these pressures. The number of gas washes can aid in reducing residues, but can also make the cycle time longer. Aeration temperature impacts the rate of off-gassing. Heated or forced aeration removes residues at a faster rate than ambient or passive aeration. The ISO Technical Committee TC 194, Working Group 11, has approved work on the revision of ISO 10993-7 with a targeted publication date of November 2025. Some of the items currently under consideration are reducing the body mass from 70 kilograms to 50 kilogram adult in accordance with ISO 10993-17. Additionally, potential risk assessment criteria for special populations, limited and prolonged limits that apply to all populations. Long-term limits for special populations need to reflect the patient growth over the use of the device. Possible exclusion of transitory devices like hypodermic needles from the standard. Establishment of tolerable contact limits for ocular tissue, and also clarification that tolerable contact limits are based on acute exposure. Testing of a blank control sample could become optional and used more for investigational purposes than as a requirement. Clarifications regarding extraction temperature for exhaustive extraction, inclusion of minimum aeration time for product release, additional special category devices, and clarification regarding the length of patient exposure for these devices. And finally, more guidance on the factors influencing product residuals.
Thanks again for joining us today. This concludes the webinar.